Hello everyone.
Hello.
I got all the problems. I received plenty of emails, I saw that. But that's all for problems. Good. How are you doing? How did you find the problems?
Depends on the problem.
It depends on the problem, okay. Which one were hard?
All of them are hard.
Oh, were they? Yeah.
Oh, except the final one.
Except the final one? Yeah, that's just pushing the symbols. Okay. Any in particular?
Maybe fourth one?
Oh yeah, the fourth one. Yeah. Did you, and the fourth one was the length of the code?
Yes.
Did any one of you had an idea about it? How to get it? Craft inequality? Yeah. There is a prefix code if and only if it fulfills the equality. And then it's just manipulating the sum carefully. Because you can, you have to sum over all strings. But you go like, oh, that's awkward. Some strings are, then you can say, well, all strings have a length. So I sum over all lengths first. And then I have 2 to the n strings of length n, and that cancels out one of the 2 to the... You get into a diverging series. That was the whole idea, and then you go like, oh, that doesn't work.
But you also have to show that the divergent, even if it's diverging, you still kind of need to show that, you can still bound a diverging series, right?
Mm-hmm.
Because even if a series is diverging, I can say, say it's minus 1 plus 1, I know that it's never going to be greater than 2, for example. Or
oh yeah, but it was the harmonic series, wasn't it?
Yes.
So it's like
it goes really high.
It goes to infinity. Yeah. If you play a bit more with that, I said when I presented those x bar and then x prime, I define, which is in unary you encode the length of the length, and then you put a 0, and then you put the length of x, and you can iterate this idea, and that's quite cute because you get always into some, because they're prefix codes, they're self-limiting encodings of the string x, you get into ever slowlier converging series. If you actually check by the craft inequality, what would be the sum, 2 to the minus length of the code words. And it's quite fun to play with it if you want to. But then the one that I gave in question 4 was like, you can't reach that. This is too small because it diverges. Unless you want to talk again about some questions, I think it might be more worth for me reading you and then trying to explain where some stuff where the difficulties were, if there were any. Good. Okay, what did we do last time? We saw a universal Turing machine. Oh, thank you. Yes. The universal Turing machine. So just to rewind a little bit more, we spent some time constructing an effective enumeration of all Turing machines. T1, T2, T3, and so on. It's an enumeration of Turing machine in the sense that they're all there. They're all enumerated in that list. And it was effective in the sense that if there's an algorithm basically which will take the number I and returns an encoding of Ti, where the encoding of Ti was the encoding of its rules. So this thing was computable by an algorithm. In fact, we gave it a name also. It was called M. It's not a fundamental name. It's just to be consistent with your notes, and I'll be invoking it today, this algorithm M. And we finish by defining a universal Turing machine. U. And U was able to simulate any Turing machine in the list. So any Turing machine. And how does it work? Well, it always has one input, but in this case, it's going to understand that that its input is encoding a pair of inputs, I and X. So we have seen some of those possible encodings. There are many of them. You just have to fix one. And then the universal Turing machine will have the same functional behavior as the machine I on input X. That was our universal Turing machine. Questions about it? Okay. Theorem. A universal Turing machine exists and can be constructed effectively. I'm going to give a proof sketch because an explicit construction of a Turing machine, even if it's for a boring Turing machine like multiplying two numbers, it's quite tedious and it's not really enlightening. The same applies here. Like you can open a textbook and check how they would do it, but even like most textbooks will say, no, I don't want to do it. So proof sketch. Which should be sufficient for our purposes. A lot of the job was done by building the effective enumeration. So U invokes M. As a subroutine, if you want. You know, once you have a Turing machine, you can realize, oh, I can invoke another Turing machine. Like I know we're all familiar with this now that we code, but yeah, it works for Turing machines. Also, you invoke M so that from I, it reconstructs the list of rules E of Ti. Which it saves on a portion of its tape. So this portion of its tape is going to become sort of a sacrosanct part of the Turing machine. It's not going to try to erase it or compute over it anymore. It sort of becomes the little box, the finite control, which now has the rules not of U, but of Ti. And to execute the consecutive actions that Ti would perform on its tape, U uses Ti's rules instead to simulate Ti's action on a representation of Ti's tape. I'm just going to put it like that. There's various ways to do it. So to execute the consecutive actions, or just the actions that Ti would perform, on input x. So u is also given x. And now it has to do, what would ti do on x? On its own tape. U uses TI's rules to simulate TI's actions simulate TI's action on a representation of TI's state content. Sorry for that. I started on the lower board today, but that's quite low.
Oh, are we recording? I asked for Lorenzo's sake.
Yeah, yes, we are. Yeah, thanks.
Cool.
Okay, so it gets the rules, it stores them, and then it will have to sort of ingenuinely manage its own tape. U is going to be managing its own tape, but there's a lot of space in its own tape. And part of its tape is going to be a representation of T's tape. Like, oh yeah, this is what T would get at this point, and I'm going to write it down here. And he basically simulates T this way. And eventually, if on input X, T halts, well, the computation of U halt, and the representation of the output that would be on TI's tape is going to be encoded in the representation on U's tape, and he's going to be able to read it out and maybe rewrite it so that it fulfills our notion that its head is sitting there. It's going to produce it as a valid output. If TI doesn't halt, well, you will just keep on imitating TI, and so it will also not halt. So it fulfills this equation also when TI is undefined. As was observed last time, well, I stated that there exists a universal Turing machine, but in fact, there are infinitely many universal Turing machines. Infinitely many such U's. Why?
So kind of dummy states.
Yeah, exactly. That's the way to see it. Yeah. Once you build one, it has a list of rules. It fulfills a Turing machine. And by the way, as was observed by Marilena, Eleonora. Yeah, U is somewhere in this list. There's going to be T, some number, K. Actually, sometimes it's used lowercase u minus 1. And then there's going to be TU, which is equal to U. And, it continues. It's in the list, U. Once you find one, you can, as Pasquale mentioned, you can make it more complicated, arbitrarily more complicated with random rules that are not even followed or that are followed for no reason. I create like a loop of 17 steps and then I exit the loop and then I keep doing my stuff. And then you can And it's gonna, from there, it's gonna create another Turing machine, which is gonna fulfill universality. It's gonna fulfill this criterion. But you realize that there's infinitely many of them. More interestingly, there's also, you know, more clever ways to simulate the machine, or you know, like that are genuinely different universal Turing machines than the one that we've been constructing. But it suffices to at least construct an infinite list of dummy universal Turing machines from one to be able to realize that this holds. Questions?
Is there any other reason we would use the undefined symbol other than a non-halting Turing machine?
Not that I see. I mean, generally in mathematics it could be used. You know.
Yeah, I mean,
but in this piece here, not that I see. No.
Yeah, because either it halts and then it has a finite string as its output, or it doesn't.
Correct.
Okay.
Yeah. Okay. If this is good, before we continue with the theory, in fact, it's actually continuing with the theory, but one might say it gets a little bit more philosophical. I think it gives depth and importance to studying Turing machines. Because one could say, and that's going to be probably the topic of the next hour, perhaps, why Turing machines? Right, the section in which we are is computability theory, and now I presented one model, Turing machines. Why Turing machines? As one can understand, why not another computational model?
Why not using lambda calculus, for example?
Lambda calculus, yes. Lambda calculus is one that I have named. I said that also in 36, Church was coming up with this. In fact, in the 30s, it was being developed. And yeah, we're going to get there. Things to remark. Yeah, this is important. So the set of functions n to n that can be computed by Turing machines I'll stop my sentence here for just a second. You recall the set of functions n to n. We saw last time there's uncountably many of them. There's only countably many Turing machines. So the set of functions that can be computed by Turing machines is countable. We gave that set a name, by the way. It's computable functions. You know, a function was computable if it could be seen as being computed by a Turing machine. So it's only a tiny sliver of the set of all functions that are actually computed by Turing machines. It forms a set. I don't give it a name. Sometimes we see this set being called C of T. I have seen that. The set of functions that are computed by a Turing machine. But it's a precise set. And it happens that this set is exactly equal to the set of functions that can be computed by many other things. Lambda calculus, we saw. That's an old model of computation from the 30s. There's another one also quite old from the 30s also, in part developed by Gödel. General recursive functions. So general recursive functions is a model of computation. It gives you a list of things that you can do to manipulate integers. And yeah, it has this algorithmic flavor. But now what I'm writing down here is the set of functions that are computed by a Turing machine is exactly equal to the set of functions that are computed via lambda calculus. And it's exactly equal to the set of recursive functions that are computed in the method of general recursive functions, which I cannot even tell you exactly how it works. Check the Wikipedia page if you're curious, but after the point I'm making here, we're going to realize, oh yeah, might as well just study one model of computation. And many others. Python, and C, and Lisp, and Java, and many programming languages. Almost all, the programming languages that we use are as powerful as Turing machines in the sense that the set of functions that they compute is the same. Now, again, you remember we had to be precise in defining what do we mean by the function computed by a Turing machine, because the Turing machine was defined in terms of bits as input and bits as output, but we defined a way to understand the end-to-end function. The same holds in Python. One might say, how do you see an end-to-end function in Python? I'm writing code with letters and so on. But there's a way to, embed functions that are of the form end-to-end. And again, it might be a bit playing with details, but one could then see that, oh yeah, Python as a programming language computes a set of functions from naturals to naturals. And then I'm just claiming here that it's equal to the set as the functions computed by Turing machines. But it doesn't stop there. Like by accident, there's also other models of computation that compute the same sets of function as the Turing machines do, namely tech happens to compute that. Conway's game of life that is an automaton, Conway's game of life. It's a 2x2 grid.
Isn't tech a markup language? I mean, isn't tech a markup language?
A what language?
Markup language. Like, can you do, for example, 1 plus 2? Okay, you can do 1 plus 2, but like,
Yeah,
can you do like a infinite for loop in tech?
Apparently, yeah. I learned that recently. That
It's Turing complete. Yeah.
it is Turing complete.
What is the-
This is on the almost by accident sort of Turing complete. I'm gonna put one last one, which I also find funny. Minecraft.
Actually, also the templating expressions that you can write in C++ is Turing.
Oh, is
Yeah,
it?
yeah, everything is Turing complete. Yes. But also Magic the Gathering card games is Turing complete.
Magic card games. Yes, I read that too in the
Yeah.
same wiki article. I knew that we reach Turing completeness at some point, and I looked up some funny examples. Conway Game of Life I was aware of. So Conway Game of Life, to come back to it, it's a very, very basic set of rules. You have an infinite grid 2x2, and each cell is either dead or alive. And there's I would say natural rules to say how the automaton evolves at each discrete time step. So the idea is that an alive cell will remain alive if it has 2 or 3 of its 8 neighbors that are still alive around it.
Yeah, there's a class named particle method, and we teach this.
Oh, okay, good. So you probably know it more than I do. Okay. Okay, great. Yeah, so if this one is alive and it has 2 or 3 neighbors alive, on the next step it will remain alive. If there is more than 3 neighbors alive, on the next step it will die, sort of as overpopulation. That could be the idea. Or if it has too few neighbors that are alive, it will also die. And a dead cell can become alive if and only if it has 3 neighbors. On the next step, a dead cell will become alive at that point. Like contamination of life. And then you have an initial configuration and you make it evolve. And it creates patterns. You could look it up online on some application. And it happens that, again, it's not clear how do you encode a function, in a setup of Conway's game of life. Well, you can by some method, which I should have to think about it, how to do it, but that's not the point. But it can compute function, and the functions that it can compute, the exact set of functions it can compute, coincides with those computed by Turing machines. So this can all be verified. So this is a motivation for the Church Turing Thesis. Which states that there is an objective notion of computability. Independent of a particular formalization. And by Turing's argument, it captures what is computable by a human. So viewed this way, if the Church Turing Thesis holds, then, this is why all these things are grasping basically the same thing. They're grasping this objective notion of computability. And Turing machines then just become one representative of the notion of computability. Turing machines are I'm going to put a convenient representative of this notion of computation, of computability. Just of this notion, it should be clear.
So if I had my own notion of computability, or my own, kind of computation, and I wanted to check that it's equivalent to all of these, I can see that one way to do that would be just reduce mine to a known one, like find a way of translating my computed functions to Turing machines or whatever. But it seems like another way, which is maybe not constructive, would just be to find a bijection with the natural numbers.
No.
Because doesn't that give me, I know that Turing machines are countable, so if I can make a bijection of the natural numbers, then I could just say this one is Turing machine 1, that one is Turing machine 2. No?
No. You can find a model of computation which computes infinitely many things, but yet not enough. Turing machines would compute more. Maybe an example of that would be starting from Turing machines, say all total computable functions. It's an infinite subset of my list of TIs.
Yeah.
Yet I don't have infinite loops in total computable functions because they're defined on each input. So I'm losing some power. There are very interesting functions that are partial computable. So it's not because something equals infinite and I have reached infinite, then their two things are equal.
I'm confused because it seems like if you have two sets that are countably infinite, you should be able to make a bijection between them. It seems like we're somehow implying that there's a smaller infinity than the natural numbers.
Yeah. You are right that you can have a bijection into them. But it doesn't mean that it can compute all functions. Look, maybe more. How many functions of the form my variable will be x. I map x to the n. N is an integer. How many such functions do I have?
Countably many.
Yeah.
Infinitely many.
Correct. And there are subsets of the computable functions. Each function like that is computable. It's like raise x to the power of 2, or raise x to the power of 3, or raise x to the power of 4. Yet I'm missing almost all computable functions. I cannot even add one. So what I'm displaying here is a countably infinite set of functions, but it's a strict subset of the computable functions.
I mean, you can do the same with subsets of the natural numbers, right? It's all multiples of 2 form a set of numbers, but they're not all the natural numbers.
Exactly.
Yeah, but that's like just because you can look at them as a subset doesn't prove that they have different size. Like the thing is, if you can make a bijection, then you know they're the same size. That doesn't guarantee that all functions between them will be bijections.
But the thing with the bijections, there are many Turing machines that compute the same function, right? Mm-hmm. So that it's kind of independent. If you can count your Turing machines and count the your own machines that you've invented, and you can create a bijection between them, it doesn't say anything about the function that they can compute. Or how many functions they can compute.
I guess it's somewhat simple in the end. Like two sets may have the same size, but that doesn't mean that the two sets are equal. What this states here is that the set of functions that are computed by Turing machine is equal, not has the same size. It's equal as this and this and this and this and this and this. The set of primes is not equal to the natural numbers. But the set of primes has the same cardinality as the natural numbers.
Yeah, okay, I don't want to take up more class time. I'm still hung up on this idea because it seems like I can correlate the primes to Turing machines. I just take the first prime and set it to the first Turing machine.
You can label all your Turing machines with primes because you have enough labels. You have incountably many primes. That's not a problem.
Okay, we'll talk about this at the break. I don't want to take up class,
but think of those. This is an infinite set of computable functions, yet it's not all computable functions. Okay, yeah, but pursue that. So where was I? I think I'm gonna go downstairs. Okay, so in the philosophy of Church Turing Thesis, that Turing machines are a convenient representative of this notion. Also, the argument that this objective notion also encompasses what humans can do, was made via Turing machines, because Turing machines was conjectured to be a faithful model of what humans can do with pen and paper. So we have Turing machines here. Now I have a definition. I have been using the word, and some people among you have been using the word Turing complete. I think it's good to define it. A system of symbolic manipulation such as computers' instruction sets, such as A, computers, instruction sets, a programming language, or a cellular automaton, okay, so I'm basically naming some of the stuff that are coming up here. I qualify them as generically a system of symbolic manipulations. You have symbols, and they evolve. You can manipulate them according to some rules. Turing machines is one of them, but all of those are other kinds of them. So those, a system, singular, is said to be Turing complete or computationally universal if it can be used to simulate any Turing machine. Okay, so that is how we prove the equivalence of the sets of computed functions. We cannot check all functions one by one and say, oh yeah, the two sets are equal. What we have to do is, with general recursive functions, for instance, well, you can show that general recursive functions can be simulated by Turing machines. So whatever general recursive functions do, well, the Turing machine can do it also. And vice versa. So the general recursive functions, you can study them and look at them, and eventually you can say, oh wow, I can simulate a Turing machine with that. And this is how you can say, oh, so everything the Turing machine can compute, general recursive functions can also compute. That is how they realized that Conway's game of life was computationally universal. By playing with the rules, you know, you can play with it and have fun, and then define gliders, which are objects that move left to right. And then you can define cannons, which are objects that are throwing gliders. Then you can define like fancy objects. I say define, but what I mean by that is you set up a configuration of alive and dead squares, and you realize that it creates a cannon, which throws gliders at every certain amount of time steps. And then you can use the gliders to, you know, do exactly what a Turing machine does. It has a head, it has a tape, and it simulates a Turing machine this way. So that the input of a Turing machine would be embedded in the input of a game of life for a universal Turing machine. Yeah, I said if it can simulate any Turing machine, one way to do that is just to simulate one Turing machine, namely the universal Turing machine. Implicit in that definition is that the symbolic manipulation, the system of symbolic manipulation is not going to be stronger than Turing machines. You know, if you assume that the system is not going to be stronger than Turing machines in terms of what it can compute, what you want to show is that it's at least as strong as Turing machines, so that it can simulate Turing machines. Computationally universal is the other. I'll come back to stronger than Turing machines later. This would be a good moment to pause. All right. I'll come back to a question of 2 courses ago. Was or is Turing paper more math or physics? I wanted to defend the case that what Turing does has the spirit of physics in some sense, and that it uses mathematics to formalize a system. And in that case, the system was a mathematician with a pen and paper. And I will go back to it to push the idea a little further. See where it leads. You may not like it. Not trying to convince you beyond what I will present here. But I guess my goal is to give a bit of a more insight on the Church Turing thesis from a physical perspective. A quote that I enjoy, I mean, I could read it many times, is the following one. Computers are physical objects.
Neumann?
Nope. On that first line, it's very hard to disagree. It's true. I mean, yeah. And computations are physical processes.
Okay, second guess, Deutsch.
Yes, well done. Well, that too, right? Once you engage a computation, you launch a process on your computer, physical process. In the case of our computers, today's computer, it's electronic-based process, but then the current will carry its own thing, and it will halt or not, and it's going to give us an answer. So what computers can or cannot compute is determined by the laws of physics alone. And not by pure mathematics. End of the quote. And Will guessed it right. It's by Deutsch. David Deutsch. So yeah, computers are physical objects, computations are physical processes. So on the question that is old, the old question of what can and what cannot be computed, Deutsch argues, well, it's a matter of physics. It's a matter of the laws of physics. What do the laws of physics permit us to harness, as processes in which we can use those processes for computation? So his version of the Turing Thesis, he calls it, by the way, the Turing Principle. But it's more accurate to say that this has been coined by Deutsch. And some people actually also call it the Turing-Deutsch Principle. Is the following. It is possible to build a universal computer. Namely, a machine that can simulate to arbitrary accuracy any physical process. So let's for a moment forget what we know about computation and forget what we know, the tradition that computation has had in mathematics, and just think about physics. If we accept this idea, well, let's first state it again. It's possible to build a universal computer or a universal machine, if you will. Doesn't even need to have the name be a computer for now. A universal machine, namely a machine that can simulate to arbitrary accuracy any physical process. Well, first I'll defend it. I have friends who have done their PhD in astrophysics. They studied the sun. And they spent their whole thesis on their computer simulating the sun. So it's quite common that in physics, once we want to study physical systems, we investigate it through another physical system. Another idea that I like is we ourselves are a little bit like that. When we want to understand what would happen if I drop my pen, well, I will build a representation of that pen falling, and I will sort of simulate that. I could, have a very coarse-grained simulation if I just think of the pen. I could be more detailed and symbolic if I want to represent the laws of motion governing the pen. But no, so suppose that it holds, that the universe is really such that, A, it is possible from within the universe to build such a machine, and that machine is what? Is one that can simulate to arbitrary accuracy any physical process. Well then, coming back to that, computers are physical objects, and computations are physical processes. The corollary is that it's possible to simulate any computation. Because computation is a specific kind of physical process. It's basically a physical process that one has elected to call a computation. Yeah. So if that machine can simulate any physical process, in particular, it can simulate those that we qualify as computation. And so the universal computer here is a universal computer. It simulates any computation. Matteo?
Thank you. There is something that I think must be relaxed because in the definition of Turing machine, the tape is the length of the tape is infinity. While if I take all the atoms from the universe, okay, I build up a computer, but it's limited. So I think the computational power of every real life, every real computer that exists is limited as the computational power by automata.
I like your remark. It makes me think of one of Deutsch's paper, 2013, his paper in constructor theory. He puts the finger on that problem. He says, the way they're defined, Turing machines have infinite tape. And I would like the universal computer to be built from within the universe once and for all. So it would need to be, finite. And so he changes the model in which the universal computer can carry any computation that the Turing machine could do, if provided extra paper if needed. And that basically also, once we have this, then we really have this thing, right?
Yeah.
That this only has 1 tera of memory, but if I would happen to need more in my computation, then what I could do is, change computer, you will tell me, but I could also append it with extra memory without changing the finite control of my system. So what I just said by concatenating this with the above, I'm going to write it down here. Therefore, such a machine can be programmed to perform any computation. Okay, I'd like to, support Deutsch's Turing's principle by 2 examples. And usually I like to write things in details and so on. I guess for those I might truncate what I write down because, I don't want to be filling up 5 blackboards and holding us back so long. So I might be a bit more coarse-grained in what I write down and what I just say. So, first example, the Zeno machine, or Zeno Turing machine. I'll just call it the Zeno machine. So think of a regular Turing. We have in mind the regular Turing machines. It has a tape. It can scan a symbol. It has a finite control. And I said that there's a background clock. There's one step of computation per unit time. And the Turing machine does one computation per unit time. Now the Zeno machine is going to hack that a little bit. It's going to say, no, I can do more. So it's a Turing machine, a regular Turing machine.
Oh, I think I see where this is going. Every half time step, it's going to do another computation.
Yeah, got it from the name?
Yeah.
Nice, good. So you take a Turing machine with extra functionality. I call this extra functionality a big step. Okay, so it can do regular steps, regular computational steps, like a Turing machine, but it can also invoke its extra feature, which is called a big step. And when the Zeno Turing machine does a big step, what it does is it's going to do one computation in a half of a regular step, another unit of computation in a quarter of a unit of time. I should have said, I said a step, but you know, my time clocks at regular interval. I have t equals 1, 2, 3, 4. I think we mentioned it. There's a background clock in Turing machines. And the regular Turing machine just does one computation per step. That's also what the Zeno does, except when it enters a big step. When it enters a big step, then it can do one operation in half a step, one operation in a quarter of a step, one operation in an eighth of a step, one operation in a 16th of a step, and so on. So that after a big step, it has done infinitely many operations.
You could think of this big step as an oracle for another Turing machine that runs for all time.
You can think of it that way. Now, it can be proven that Zeno Turing machines can compute more functions than Turing machines. Once we see the halting problem, you're gonna see you can think back of the Zeno Turing machine and say, oh yeah, it could have computed it. So take it for granted that Zeno machines can compute a larger set of functions. Then I call it CT, the class of functions that can be computed by Turing machines. And also, it doesn't really look like it because I'm being a bit coarse here, but it can be formalized very beautifully mathematically. So if what you want is mathematical rigor, you know, you can define things very nicely in a nice language, and it can be very formal mathematically too. So my question is, based on what should we reject such a formalization of computation? Because if really this is a valid computational model, it's in tension with the Turing Thesis. And the Turing Thesis says that I listed a bunch of computational models and automatas and symbolic manipulation systems. And I said that they're all computationally equivalent. They can compute the same set of functions: lambda calculus, general recursive functions, Conway game of life, Turing machines. And then I come up with this annoying thing, the Zeno machine, which, you know, It sorts of, I increase its power by being able to do big steps like that. And I claim without showing, but it's going to be easy to see once we see the limits of Turing computability, that Zeno machine can defy that limit. It can compute stuff that Turing machines cannot compute. And I repeat my question, based on what should we reject Zeno machines?
Infinitely many operations.
But it's not a matter of time. I think that they can solve the same class of problem but faster.
They can solve the halting problem.
Yeah, this one
They
solves the
solve the
halting problem.
problem.
Yeah.
Just by
In a single big step, it can ask, does this machine I halts on input X by simulating the machine,
just running it.
and at the end of the step, if it has halted, it will have found it, because it has done an infinitely many steps. And if it doesn't halt, it's going to go like, no, it has not halted, but I've seen infinity. So since I have seen infinity, I know it doesn't have halted.
How long does the big step take?
Yeah, it takes one time step in this model. That's why I still have the discrete time steps, and a regular Turing machine step takes one time step. Now a big step, what I have defined as a big step here, also takes one time step by hacking time, basically, by compiling, that this sum converges to 1, right? That was the idea.
Compactifying the rest now. I'm gonna go 1,000 steps and then I'm gonna just put a drop of water inside and see if it falls quickly.
I heard one word out of 2.
Sorry, I'm just trying to imagine how do you know, how do you actually perform infinitely many steps?
You're putting your finger on something. How do you do that?
I mean, a human can't do it, and maybe no physical process can do it. I mean, that's
Yeah,
Yeah,
exactly. If you really want to keep your mathematician tuxedo and just say, no, all this church Turing thing is just pure mathematics, it's a bit hard to find arguments to reject the Zeno Turing machine. If you take the physicist's point of view, go ahead and try it. Build such a machine just for fun. You're going to have blow up in energy, or you're going to run into H bar, the Planck's constant. Your device is going to melt.
Yeah, 'cause
It's not physically possible.
it needs to move bits around in memory in arbitrarily small amounts of time. So you'd have a head that was moving super fast and heating up and melting everything and using huge amounts of energy to accelerate back and forth.
Arguments of the kind will be invoked. Yeah.
Physicists like approximations. Can it just be possible to approximate it?
Yeah, but what becomes interesting is approximating this accumulation point, and at some point you will truncate it because whatever reason is the reason. Maybe it's energy, maybe it's resolution of space, maybe it's resolution over time. But if I truncate this ... then it's no longer really a big step. What I'm just saying is that in a single unit of time, my truncated big step has done, 200 steps. Wow, no big deal. It's just a little bit faster hardware, but it no longer has the spirit of the Zeno machine, namely to do infinitely many computation steps in a single unit of time. So based on what can we reject the Zeno machine? And just the church Turing thesis like that is slightly hard, because one will say, well, it does not correspond to my notion of objective notion of computability or whatever. But invoking Deutsch's take on it, it will simply say that, well, that is not a physically possible machine. So short answer is just physics.
So the
Turing machine would be able to solve Halting problems.
Yes.
Right? Yeah. You can see with physics that you might also be able to do that, given that certain physical laws would be different. Like, for example, it's not clear that time travel, which is a thing you might be able to do according to general relativity, that you could solve the Halting problem. I mean, probably not, but intuitively it's not clear.
Yeah.
Just to add to your point.
Yeah. It's actually, with my second example, I'm going to put my finger on something, and then maybe what you mentioned would be the final piece of the cake. But Sam's idea is, oh yeah, once we start to recognize that physics is linked with computation, we can harness new physical phenomenon for computation. For example, if looping around a black hole in a certain way allows us to do that, well then we'll have to update our notion of what is a universal computer. And we're going to harness that phenomenon to solve the halting problem. It doesn't mean that we will be infinitely powerful. There's still going to be problems that are going to be that this machine runs into. So I'm going a bit beyond, but yeah. Once we see the halting problem, if you want, I can come back to the Zeno machine and see how the Zeno machine solved the halting problem, but how it also has its own halting problem. So there are problems that it doesn't halt, that it doesn't solve. So a second example. Suppose that in the year 25, a new theory of physics is discovered. And we learned that physical systems can undergo different processes simultaneously. Okay, so we learned something new. We go like, oh, physical systems can undergo different processes simultaneously. And since computations are physical processes, we could say, oh, we have a new kind of computation that is possible. We can harness this functionality that systems can undergo different dynamics or different processes simultaneously, and harness that for computation. Perhaps this functionality could be harnessed to speed up computations. Computations is written here. Due to a form of parallelism. that's, a possible idea. Now, what's the punch of the example? Suppose that in the year something 25, a new theory of physics is discovered. Physical systems can undergo different processes simultaneously. Sort of way of speaking. Perhaps this functionality can be harnessed to speed up computations due to a form of parallelism. Well, the year is 1925. It has happened in the past, and the theory is quantum theory. And the speed up is the speed up due to quantum computation.
Does it mean that maybe it's possible to build a sort of non-deterministic Turing machine at this point? Because if they perform a different process to each possible branch of computation, is that?
It's, I think, unknown, because problems solvable in polynomial time by quantum computers has a complexity class called BQP.
Yeah.
The classical one of non-deterministic Turing machines is NP, and I think it's not known what the relationship between BQP and NP is.
Thank you. This is the point. How do you call it? QMP? No.
BQP, bounded quantum polynomial time.
Okay, thank you.
Is that what you mean, though, by non-deterministic?
I think I mean quite. I'm not sure about this computational class. I never use it, but I assume that a non-deterministic Turing machine can solve at least NP-complete problem in linear time.
In polynomial time, I think. Yeah.
Yeah.
Well,
Also, polynomial time is okay for that kind of problem, but it's way.
yeah, it's always tricky because non-deterministic Turing machines, it's like with the way it's defined is always a bit awkward. Like, what's the complexity? Because you explore the tree of possible choices, and you say, oh yeah, it's an NP if one of the branches is in P. Yeah. But if you see that the tree is explored probabilistically, then maybe the chance of you falling on the right branch is very, very small. So
in fact, I don't know.
So it's not like, you can harness like a probabilistic version of a quantum machine to then solve efficiently problems that are in P. It's not exactly the same.
Yeah, I think the notion of non-deterministic Turing machines is not that it probabilistically explores the tree, but that it explores every branch simultaneously.
Exactly.
You go in and you put in a sort of big OR at the end, and you get it.
So it's hard to really see how I would use it.
No, because in general, for us, it's cheating. You cannot use a non-deterministic, but maybe I don't know.
No, exactly. No, it is still cheating. I prefer to define NP through the witness. You have a witness, and that helps you to verify the solution efficiently. But that is not related to NP. This is just a story that I told you. Suppose we find that in new physics we harness this phenomena to use a form of parallelism to speed up computation. I said, the year is 1925, in fact, and this theory exists. It's quantum theory. And the speed up is the one due to quantum computing. Now it's worth connecting the dots between that example and the discovery of quantum computing with Deutsch's notion of the Turing's principle, because he connected the dots in the very same paper. Deutsch 1985. 1985, yes. By understanding computation physically, Deutsch came up with the universal quantum computer. And in fact, his 1985 paper is titled Quantum Theory, the Church-Turing Principle, and the Universal Quantum Computer. So I recommend, if you like, it is in my reading list, in my recommended reading list. You could find the paper somewhat very easily online. But have a look at section 1. Okay, it's also the informal section in which you can appreciate his defense of the Church-Turing thesis as a physical principle. And also in the rest of the paper he explains how, well, if computation is to be physical, let's use our best physical theory to build computation, namely quantum theory. And you can speed up computations. Actually, yeah, it's proven for sort of boring problems, but it's always very hard to prove the results between different complexity classes. But if you're curious about it, look at a course on quantum computing. Now what I should say is for this course though, I'm interested in what can and what cannot be computed. And the universal quantum computer does not change that, because a universal quantum computer can be simulated by a Turing machine with a waste in time efficiency, but I don't mind about time efficiency when it comes to algorithmic information. So I think it's good to mention it, because for me it's hard to tell you about the Church-Turing thesis without telling you about the underlying conjectured physical principle, especially since it has a consequence on connecting it with quantum theory and quantum computation. If you want more of that, you can look at Deutsch's book, The Fabric of Reality. Chapter 6. Chapter 6 is on the Turing principle. Questions about that?
Is there any sort of competing train of thought, like what else might be protecting the Turing thesis, if not something like this?
Yeah. I have looked hard for a precise meaning of the Turing thesis. In fact, most of the people will say, it's sort of quote unquote empirically verified by the fact that every time one come up with another idea of formalizing computation, he realizes that, it's as powerful as Turing machine. As I said, sometimes it's unsatisfactory because I just came up with Zeno machines. I didn't come up with it, but I tell you about it. It's very formal too. You can formalize it, and it's mathematically precise. So mathematics alone cannot tackle it. I don't have a good answer to say. It's probably because I'm also trained as a physicist. I have embarked on David Deutsch's boat of it is a physical principle. And and those funky Zeno Turing machines, they sort of make me think of back in the days, people were trying to make so-called perpetuum mobilum, a machine that harness energy, from. And once you look at the design, it's sometimes very awkward to try to refutate, like, oh, where's the catch? Like, no, you cannot generate energy from nothing. So you look at it, where's the catch? But if you take the principle of conservation of energy seriously, you go like, no, just such machines don't exist. And there's a very analogous take here, because if you take Turing's principle very seriously, you'll say, well, no, it's a well-defined, unique kind of universal computer. Now, as Sam mentioned, physics is open. I wanted to tell you about the last piece of the cake. This is 1925, it's quantum theory. Still, it took 60 years to actually realize, oh, wow, let's connect that to computation and build the universal quantum computer. I must say that Feynman in 82 made some progress, and basically Deutsch wrapped it up in 85. But yeah, so if in 100 years from now we harness black holes in a way that was unpredicted, and we realize, oh, some phenomena allow us to not only speed up, suppose, but change the class of computed functions, well, then what we will have to do is then build hardware like this one, harnessing that phenomena and using it to simulate other computations, because we might be able to, enlarge our class of computations. And we will be thinking back of the year 2023 and saying, oh yeah, we thought we had the universal computer, but no, we did not yet have it. Yeah. Logically, nothing prevents the class of functions to be enlarged by harnessing new phenomena like time travel or things of the kind.
So, similar to how you were saying the Church-Turing thesis is sort of verified empirically, you could say the same thing, and I guess this is sort of the point you were making, you could say the same thing about conservation of energy.
Mm-hmm.
I know Deutsch and many other people are not a fan of induction, but there's a sense in which conservation of energy we don't know it to be true, it's just that it's never been proven wrong, and it's been subjected to, a million tests in all kinds of different ways, and it's always been seen to be true. So now we take it as a kind of assumed principle underlying everything, that it's true, and that these perpetual motion machines can never work.
Exactly.
But who knows, maybe 300 years in the future someone will find one,
and
physics will turn on its head.
It's not just the inductive idea of like, oh yeah, we've checked it many times, but it's also, I think, it's the problems that it has managed to solve. So conservation of energy was so important that once in some reaction, the beta decay reaction, it was observed that energy was not conserved. So people were like, whoa, that is really weird. Did we make an experimental mistake? Maybe that could have been the case. No, really, like, according to the energy of the input particles versus the energy of the output particles, we lose some energy. So, Sam, was that Pauli who conjectured that?
I think so, yeah.
And Pauli said, well, it's probably because a new kind of particles has been emitted in that energy, and it carries the lacking energy. It was so strong, the principle of conservation of energy, that he preferred to say that we're lacking a piece of the puzzle in terms of the output particles. And this is how he found neutrinos.
I doubt that was Pauli. Well, maybe I could, yeah.
Fermi.
I don't know who came up with neutrinos. I don't remember.
Yeah, so it's more than just verifying the theory. It's also using it as a explanatory framework to build new theories.
Fred Reines.
Reines?
That's what the Google says.
How do you spell it?
R-A.
Neutrino was postulated first by Wolfgang Pauli in 1930 to explain that.
Oh, okay.
Yeah. It's a good point to stop. Next time we are going to jump back into the theory. We're going to see decidable sets, recursively integral sets, and some classifications of them, probably semi-computable functions. And we're stepping somewhat steadily towards algorithmic complexity.